Alright guys, this problem is crazy as shit, like legit crazy as hell. So let's go ahead and get started, right? They give you EALs, you gotta find some lengths, but that's not a problem. We gotta find stress, forces, nodal displacements, and verify force equilibrium at two nodes, and we have to use symmetry. So let's go ahead and get started. Alright, so I kind of already laid all this out, right, just to save time because this problem is very long. I want to go ahead and found the length of these two bars, right, that go this way because we're going to need them. So everything's 3 meters going sideways, 4 and 2, and 1 and 6 are also 3 meters. So these two right here, you do Pythagorean theorem, right, 3 squared plus 3 squared is equal to something squared, which is just radical 18, and that answer was 4.24. So that's the length for bars 3 and 5. So we have 6 elements total. So it's using symmetry. So we're gonna cut it down this way, right? The reason we do this way, right, is because it's all perfectly even, right? It's pretty straightforward. So what happens is this 100 kilonewtons gets cut into 2. Okay, just keep that in mind. And the area of this bar gets cut into 2. So the area from nodes 3 to 4 gets cut into 2. So just keep that in mind when we do EA over L, when you start doing the verification of forces, all that good stuff. But for now, we just continue like we would otherwise, right? We're using this matrix for stiffness values for each element, right? 1, 2, 3, 4, 5, 6. We got to determine the angles. I'm not going to go into depth how to determine the angles here because it's too much time. Just check the other videos though. I explain it in problems 330, 329, 327, and I think a little bit more, right? So for the first element, I like to go from the small node to the big node. This is the first element right here, so it's 1 to 2. That angle is 90 degrees, right, from the positive x-axis. Let me draw your axis. So that's going to be 90 right here. If you get the cosine of that, you will get 0. Sine of that is 1. Cosine squared is 0, sine squared is 1, and cosine times sine is 0. For elements 2 and 4, they're the same, right? They're from 1 to 3, from 2 to 4, you're going from small to big node. So the same angle, right? 0 degrees. So for elements 2, 4, we're going 0 degrees. And let's make a note of that. For the first one, we went from 1 to 2, so we're going to make that note 1 to 2. For the second element, we went from 1 to 3, so 1 to 3, and element 4 from 2 to 4, 2 to 4. All right, so cosine of 0, that is 1, sine of 0 is 0, cosine squared is 1, sine squared is 0, cosine times sine is 0 for both of them. Element 3 now, we're going from 2 to 3. That angle from the positive x-axis is negative 45. Or just 45 degrees, whatever, right? No, I mean, in this case, it has to be negative 45. But I mean, on the diagram, I didn't really have to draw a negative. That's just 45 degrees. That's for element 3. That goes from, again, 2 to 3. So we're going to make that little note, 2 to 3. And take the cosine signs. We will get radical 2 over 2. Negative radical 2 over 2. What else? We'll get half when we square cosine. We'll get half when we square sine. And we will get negative 1/2 when you multiply cosine times sine. Next one, right? Element 5. Almost there. Again, that's from 1 to 4, from small to big node. That's a positive 45 degrees. So we will put positive 45 degrees here. That's radical 2 over 2, radical 2 over 2, right? Just take the cosine and sines, nothing crazy, half, half, half. Verify all this, right? I'm assuming you know basic trigonometry. So, and that one goes from element 5, it goes from 1 to 4. So we're gonna go ahead and put 1 to 4. Next one, finally, element 6. It goes from 3 to 4. So element 6, 3 to 4. That angle is positive 90 degrees. So just like the first one's gonna be 0, 1, 0, 1, 0. Cool. So we could go ahead and get the EA over L numbers. I'm sorry if it's a little sloppy. It's just too much writing today. I'm kind of exhausted, but it's all good, right? So do EA over L for the first element. So they all share the same E and the A, except this one. Remember, it got cut in half. We mentioned over here, but just keep that in mind. First element, EA over L, the length is 3, E is 70, A is 3 right here, so it's 70 times 3 over 3, that's 70, times 10 to the 5th, right? This is G, 10 to the 9, negative 4, they're all going to be 10 to the 5th. Let me go ahead and write that here. So you can just focus on the big numbers. Okay, 10 to the 5th. So the first one was 70, right? 70 times 3 over 3, that's 70. Next one, 2 and 4, same thing, right? They're both 3 meters, so this one's also 70 for both of them. Number 3 is 70 times 3 over 4.24. That's going to give you 49.5. Same thing for element 5, right? It's also 4.24 in length. So that's also going to give you 49.5. Now this one's not 70. It's 3 meters long, but we get half of it. So half of 70 is going to be 35. Okay, cool. So we could go ahead and start filling in the matrices, right? For element 1, we get the EA over L. 70 times 10 to the 5th. And that goes from 1 to 2, okay? So it's U1, V1, U2, V2. Same thing here, U1, V1, U2, V2. And that's going to be cosine squared, sine squared, cosine squared, sine squared. So we'll get these two numbers, 0 and 1. So it's going to be 0, 1, 0, 1. Cosine times sine is 0, 0, 0, 0. I'm just using this matrix. That's going to be a 0 up here. It's 0, negative 1. Symmetrical, so the rows become columns. 0, 0, negative 1, and 0. Cool. I'm kind of speeding through this because I'm assuming you know how to do this stuff. This isn't the hard part. The hard part comes a little later. But K2, right, element 2, that's 70 times 10 to the 5th times 10 to the 5th. That is between nodes 1 and 3. So it's U1, V1, U3, V3, U1, V1, U3, V3. And there's a reason it's U1, V1, U3, V3, not U3, V3, U1, V1. But watch the other videos if you want to know why, but I'm assuming you know why at this point. So cool, let's go ahead and continue, right? We're using cosine squared and sine squared, so it's 1, 0, 1, 0. It's gonna be 1, 0, 1, 0. Cosine times sine is 0, so it's 0, 0, 0, and there's a 0 here. Then it's negative 1 and 0. Rows become columns, blah, blah, blah. We got 0. Cool. So that's that one. Now let's continue. K3, third element, that is 49.5 times 10 to the 5th times 10 to the 5th, and that is between nodes 2 and 3. So it's U2, V2, U3, V3. And again, right, U2, V2, U3, V3. All right, so continue, right? C squared, S squared, C squared, S squared for element number 3. That's half, 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 half. Half, 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 half. Next one is cosine times sine. It's positive, negative, positive. So the sign switch. Negative 1/2, positive 1/2, negative 1/2. Then C squared, S squared, but negative. So it becomes negative half, negative half. And then finally, negative CS, but it's already negative here, so it becomes positive. Okay, there you go. Rows become columns, right? Symmetrical. Negative half and half. Half, negative half, negative half, and that's it. K4. We're going to use 70 times 10 to the 5th. EA over L. And that is going from 2 to 4 for element 4. So U2, V2, U4, V4. U2, V2, U4, V4. Okay? Cosine squared, sine squared, all that good stuff, right? So it's 1, 0, 1, 0. Diagonally, 1, 0, 1, 0. And then we're going to plug in, what is this? CS. So it's, oh, right here, 0. So it's 0, 0, and 0. And 0 up here. That's going to be a -1 and 0. So 0, -1, 0. After a while, you just know the tricks, right? It's too many problems. You'll get the hang of it. K5. Element 5, that is 49.5 times 10 to the 5th. Times 10 to the 5th. And that is between nodes 1 and 4 for 5. So it's going to be U1, V1, U4, V4. Same thing up top, U1, V1, U4, V4. All right, cool. So cosine squared, sine squared, cosine squared, sine squared. For element 5, that's half, half. Well, everything's half. All three, right? Half here, half here, half here. So what we're going to do is just follow the signs here. So it's half, half, negative half, blah, blah, blah. So it's half, 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 negative half, half. That becomes negative half, negative half, and negative half. Rows become columns, negative, negative. And the reason I don't factor out the half to make it look nicer is because I'm going to switch it up anyways in a second. Finally, element 6, right, goes from 3 to 4. So we're going to go U3, V3, U4, V4, U3, V3, U4, V4, and the stiffness is 35 times 10 to the 5th. All right, cool. Throw in the numbers, right? C squared, S squared for element 6, so it's 0, 1, 0, 1. Diagonally 0, 1, 0, 1. Then the cosine sine, that's 0, 0, 0, 0 up here. Then it becomes 0, -1. Yep. And rows become columns, so 0, -1, 0. So cool, we got it. So before we do I already have it ready, right? The global equation. But let's start applying the boundary conditions, okay? So U1, so this is what happens, hold on. When you do symmetry, you make assumptions. There is one assumption that's really important. I'll move that over there. So this is your little diagram. I'm gonna do it right here, squeeze it in. So we're gonna cut it this way, right? So it becomes a perfect square now. Ooh, not the best square, but that's what our diagram looks like, right? This is half the area, half the load up here. But what happens is this is fixed right here, okay? That's no movement in the X or Y direction. But what happens here is you make an assumption that since you're analyzing this and you only have one force going down, you're gonna assume it's not moving in the X direction. So you make a roller. And if you remember what a roller is from statics, hell, I didn't remember until I looked it up maybe an hour ago. But it only moves up and down. It's a roller, right? It doesn't move in the positive or negative X-axis, only in the Y direction. So that means that apart from U1 and V1 being 0, boundary condition, that means your U4 is node 4, right? And your U3 are 0 as well. Not the V's, just the U's at 4 and 3. So this is what we're gonna do. Let's apply that boundary condition. I'm gonna go ahead and make a little note right here. Sorry if it's a little all squished up, but U3 is equal to 0 and U4 is equal to 0, okay? That just means that's an assumption we're making. We're analyzing this beam, this structure as an engineer, and we're like, okay, look, if we're pushing down and it's symmetrical, I'm gonna go ahead and assume that there's no movement in the X direction. There probably is. If you saw the other problem, 330, the one we just did, that one there was, but it was very little. You remember it was like 1/3 of a millimeter. So think about how small that is. It's negligible, right? So that's kind of why we do this assumption here, and that helps us with the boundary conditions. So U1 and V1 are all fixed. So U1, V1, right? There's a U1, V1 here. Where's it? Right here. Let me move it up. And that's it, right? Now the rows too. U1, V1, U1, V1, and U1, V1. Okay, that's one of them. Now, U3 and U4. So anywhere you see a U3, that goes away too. U3 here. Right here, what do we see? We see a U3 here. U4 and U4, not the V's, remember, just the U's. That's the assumption. U4, and finally U3, U4, U3, U4. So let's go ahead and cloud. You see, this is why I like to cloud. I mentioned it in the other videos to see what are the important values. Okay. Now, you could hold off on clouding actually. I should have waited, but whatever. I'm already in too deep at this point. Wow, all these. So hold on, I'm not gonna cloud these yet. But, oh, and these either. There's a lot of them. So this one and this one. So I am gonna cloud them eventually, just give me a second. But before we could add the matrices, remember, they have to have the same stiffness value outside. So 70, 70, that's the same. You could add these, but you can't do it with this one, okay? You can't do it with this one either. This one, with this one, yeah. So these three could add, but you gotta alter. What I like to do is just make them all look nice and neat. I like to have 10 to the 5th outside for each one. So we're gonna throw all the numbers in there. So 70 times these four, 70 in this case times this one only, 49.5 times this one only. Oh, I mean all these actually, all these ones, yep. 49.5 times this one, 70 times all of them, 35 times all the four. So that's what we're gonna do, right? If we do that, you're gonna have a 70 here. So that means this goes away, right? The other ones are 0, so it doesn't matter. There we go. What about this one? 70 times 0, that's just 0, so that just goes away. Okay, what else? 70 times all these, it's just this one. So this one goes away because the rest are zeros, right? There we go. That makes it look nice. 35 times all these, so damn, it's a lot of erasing, but that is how you do it, you know? It is what it is. So 35 times all of these, it's 35, negative 35, negative 35, and 35. Okay, so 35 goes away now. And 49.5 to this one. Okay, that's gonna be 24.75. Okay, and finally all these, shit. So I'm gonna go ahead and pause it and just continue, right? I'm gonna, to make it short, but 49.5 times every single half. That's not crossed out, okay? All right, cool, so that's it, right? I just multiplied 49.5 times every single half. So the signs are correct, but just verify them yourself just to make sure, right? But yeah, and then the 49.5 out here goes away, so that's a nice 10 to the 5th. So everything is now 10 to the 5th outside. I forgot to erase this one. But yeah, now we're good. All right, the video cut off, but so we're good, right? We could go ahead and add the matrices since they share the same 10 to the 5th outside. So that means we could just add the numbers inside each matrix. And we do that. I just want to go ahead and did this. The video was playing and I didn't feel like erasing it, but we just applied the boundary conditions just like we did here, remember? When we crossed out, it's the same thing you do for the global equation. So U1, V1, U3, and U4 are crossed out, rows and columns. So that means we care about this 4x4 matrix, U2, V2, V3, V4, and same thing going down. So let's go ahead and do the first row for U2. and then you could do the next 3 on your own. But I mean, I'll give you the numbers anyway, so you could verify and make sure you're doing it right. But it's just a long video. So U2, let's look for all the positions that U2 has. So we have one right here, right? There's a U2 right here. There's one right here. There's none here. There's one right here. Nothing here. Nothing here. So 24.75 plus 0 plus 70. That will give you 94.75. Now let's do U2, V2. U2, V2, there's one right here, there's one right here, and there's one right here. So 0, 0, negative 24.75. This is going to be negative 24.75, right? Cool. Next one, U2, V3. So let's go to the U2, V3s. There's none here. There's U2s, but there's no 3s. So go to the ones at 2 and 3 right here. None here either, okay? U2, there's only one right here. 24.75. That's the only one. So 24.75. And finally, U2, V4. You search up all the U2s, V4, there's none here. There's none here, right here. U2, V4, there's a 0. And there's nothing else. So that means this is a 0. So do the same thing for the rest. I'm gonna pause it and then just fill them up and then replay it, but just make sure you know what you're doing. You're following what I'm saying, okay? All right, so this is what it should look like if you did all the math correctly. Now, there's really no way to verify this is correct. It's kind of just trust your gut, but you know, just kind of looking at it, it's kind of symmetrical, right? 94.75, 94.75, 59.75, 59.75, then 35 on both sides negative, then 0, 0, 24.75, 24.75, positive. It's like symmetrical if you see it. So, I mean, that doesn't verify you did it correctly. It just so happens to be the case, but usually when you notice some patterns like that, that means you're probably doing something right. But don't take my word for it on that. Just that's just maybe something you should notice. And then I also forgot to put 10 to the 5th out here. Remember, they all share the same 10 to the 5th. Now, I usually solve these problems. What step is this? This was step 1. This was step 2. This is step 3. And I usually solve these problems using algebra, right? System of equations. But to save on time, I'm not going to do that here. I could do it, and it's 4 variables, so it's kind of complicated, but it's not really complicated. It's just pretty long. So, and I'm assuming if your professor has one of these problems on the exam, he's either one, gonna let you use your graphing calculator if you have one. You could solve matrices on them, I think, right? I never had one, but I'm gonna be honest, I took this exam. Well, the first exam I took it in class, but it wasn't complicated. This was part of the second exam, so yeah, it was complicated, but I was lucky. I was COVID. I took this class during COVID when it hit March 2020, and I made a crazy ass MATLAB code to solve all this. All I had to do was input the numbers, and not only it would solve me this, but it would solve me the whole problem. It was I took time on that MATLAB code, and I probably have it. I just gotta find that shit. It's in one of my flash drives, though, but yeah, just I guess I got lucky in that sense. I finished the exam in like 30 minutes. It was an hour 15, and so yeah, I mean, these are the numbers you get. So hold on, before I just gave you the numbers, but so you're probably looking at the screen right now. Obviously, this is a screenshot of a calculator for system of equations. To find it, it's pretty simple. Just Google system of equations calculator. In this case, it's a 4x4 calculator, right? 4 variables. So just plug in the numbers, right, as you see. Hopefully I'm reading it right. I'm not looking at it right now, but just remembering it. You just plug in the numbers, right? The first row is 94.75, negative 24.75, 24.75, and 0. And you set that equal to your force. And I forgot to do it on the paper, but those force numbers right there are 0 and like 10 to the... So hold on. It was 0 for... Hold on, give me 1 second. I'm not looking at it, remember. So it's force 2x, force 2y, force 3y, and force 4y. So just by looking at the diagram, just take a look at your paper for a second. If you're doing it right, at force 2, you have a negative 50,000 for the y direction and 0 in the x direction. At force 4, you have a negative 50,000. Remember, we cut it into 2, so it's negative 50,000 in the y direction. At force 3, you have 0 in the y direction, and that's pretty much it. So, and those 50,000s, those two 50,000s, you divide it by 10 to the 5th, which is why you get negative 0.5, which is what you're looking at on the calculator on the screen. And yeah, that's pretty much it. Just set up the system like that. It's pretty straightforward, nothing too complicated, and just click calculate, and it should give you these numbers. So now we're back on the paper, right? So here you go. Let's box these in. I was going to, as I was talking, trying to fill these in, but let me just do that right now. Force 3y and force 4y, okay? Yeah, this problem requires a lot of editing. I already feel it coming. I haven't edited nothing, but I could just feel it coming. Negative 50,000. And it has to be in thousands, right? Because you're dealing with newtons. We set this matrix up in newtons per meter, so you gotta make sure this is correct. And negative 50,000. Okay, cool. So, what else we got? Well, yeah, we box these in, right? So it is what the calculator should give you if you plugged it in correctly. I think the variables were like it was like something letters, but just put them in order and they should give you these numbers. But yeah, that is the displacements. Let me go ahead and write the stress equation, the formula first. All right, there we go. So that is the formula for stress. We're gonna find because the problem asks, right, find the stresses. So we first find stress, then we can find the forces, because it's easier that way. So find the stresses, right? It's E over L, then this matrix, so 1/4, negative cosine, sine, times your displacement vector. Between what nodes did we characterize this beam? So for the first element, right, it's between nodes 1 and 2, right? Remember, we did it here because we use this angle. So we're using 1 to 2. And what else do we need? E over L. So 70 times 10 to the 9 divided by the length of 1, which is 3 meters. So that's going to be 23.33 times 10 to the 9. Okay. And then open bracket for the cosine and sine values. So let's go ahead and look at that. 0 and 1. But the first ones are negative. So it's negative 0, negative 1, 0, 1. And then times the displacement vector, right? So it's between nodes 1 and 2. So it's U1, which was 0, remember? Boundary conditions. So 0, 0, and then U2, V2. So it's these two numbers. So it's 0.00135. That is negative 0.00850. Okay, that's the first one. So let's go ahead and do the math. It's going to be 23.33 times 10 to the 9, open parentheses, 0 times 0, negative 1 times 0, 0 times this, 1 times this. So it is negative 0.00850. Do that math, what would you get? You will get sigma 1 is equal to negative 198.31 megapascals. Negative means it's in compression. And hold on, we're not done. So sigma 1 was from nodes 1 to 2, right? So from nodes 1 to 2, that means from 5 to 6. It's the same, it's symmetrical. So it's the same value. So it's also compression for sigma 5 to 6. Because technically they're asking for every single element, but that's the whole point of using symmetry, right? It saves us time, and we could go ahead and just do that. I'm gonna do 2 more this way, then the other ones I'll just give you the numbers. I'll show you the process, but figure it out on your own too, so you kind of get the hang of it. Sigma 2, so sigma 2, let's see. It's this one. The length of element of bar 2 is also 3, so we're going to have the same E over L value, 23.33 times 10 to the 9. Remember, we don't include area. Open parentheses, negative cosine, negative sine. So for element 2, it was 1, 0. So it's negative 1, negative 0, which is just 0, 1, 0. Finally, the displacement vector is between nodes 1 and 3. So it's U1, V1, which is 0, 0. And then U3, which was 0 again, remember? We made that assumption here. And then V3, we found it up here. So negative 0.013. It was actually 6, 7, okay? I don't know why I wrote, there's a 6 right there. Let me just go ahead and make sure the other ones are correct too. Yeah, cool. All right, so finding sigma 2 now, this is what we're gonna do. It's negative 1 times 0 plus 0 times 0 plus 1 times 0 plus, well, 0. Oh shit, yeah, so it's 0. This whole thing, there's nothing going on with element 2 right there. So 0 megapascals, and that's gonna equal the stress. So we're doing element 2 now from 1 to 3. So now this one's from 5 to 3. This direction also matters. So don't think that it's you could put 3 to 5 and get away with it. No, it's perfectly symmetrical, so you have to do it exactly how it's laid out. We went from 1 to 3, so now we're going from 5 to 3. Okay, just perfectly symmetrical. All right, because if you switch these numbers, 6 to 5, now this doesn't apply anymore. It's a different direction. Okay, I mean, it's kind of complicated, but I'm assuming you understand what I mean, right? So last one, right, sigma 3 is equal to E over L for element 3. Goes from 2 to 3. E is 70 times 10 to the 9 divided by 4.24. If you do the math, you will get 16.51 times 10 to the 9, and then the cosine and sine values of that. Element 3 is radical 2 over 2, negative radical 2 over 2, but the sign switch for the first ones, because, right, negative cosine, negative sine, so you'll have negative radical 2 over 2, radical 2 over 2, radical 2 over 2, negative radical 2 over 2. Okay, there you go. Displacement vector, what is that? We are between, this is element 3, so we are between nodes 2 and 3. So 2, 3, let's go ahead and do that. U2, V2, that's going to be, we got them right here earlier, right? So it's going to be 0.00135, then it's negative 0.00850. Now U3 was 0, remember? That was the assumption. Was it between nodes 2 and 3? Yes, it was. Cool. So 0 and V3. So that is negative 0.01367. Let me go ahead and label them real quick for you. So this was a U2, V2, U3, V3. These, what was it for element 2? It was 1 to 3. So this was U1, V1, U3, V3. Then for element 1, that was between nodes 1 and 2. So it's U1, V1, U2, V2. That's just what we're doing, okay? Just stay consistent. We're doing good. Sigma 3, do the math. What I like to do here, just factor out the radical 2 over 2. So you're going to have negative 1 times this, plus 1 times this, plus 1 times this, plus negative 1 times this. Multiply by radical 2 over 2, because you factored it out, remember? Multiply by 16.51, multiply by 10 to the 9. If you do that, you will get 44.60 megapascals. Positive, so that's in tension. And which one is that equal to? Well, let's see. Sigma 3 was between nodes 2 and 3. So 2 to 3, now it's from 6 to 3. Okay, so sigma 6 to 3. All right, so I'm gonna go ahead and just give you the other ones. I'm gonna show you, but you can pause the video if you want to see it. But oh man, all right, so this is the one I already did, right? So we just got sigma 1, sigma 2, and sigma 3. Now we're gonna get sigma 4, sigma 5, and sigma 6. I didn't plug in the numbers, I plugged in the vector, right? It's U2, V2, U4, V4 for sigma 4, U1 to node 1 to 4 for sigma 5, and then for sigma 6 is 3 to 4. So those are the answers, but I'm gonna go ahead and write them down right here. Forget you saw the top piece of that. I mean, I'll explain it in a bit, right? That's the next step. So that means sigma 4 is equal to negative 31.50 megapascals. That is in compression, right? And it's equal to sigma from 6 to 4 on the other side of the beam. All right, sigma 5 is equal to, what is that? Negative 191.23 megapascals. That is also in compression, and that's equal to sigma of 5 to 4. Last one, sigma 6 is equal to negative 63.22 megapascals. That is also in compression, and that's also equal to the other side of the truss system, symmetrical, 3 to 4. So those are your 6 stress numbers. All right, so now the problem says find the forces. Okay, so forces is easy too. This is what we do. This is step number 6 in this sheet. So we know force is equal to sigma times area, right? And we know the area is the same for all of them. It's 3 times 10 to the negative 4 meters. Okay, that's gonna be, so that's cool. So area is the same for all of them, except one of them, remember. It was from 3 to 4, nodes 3 to 4. But let's go ahead and continue, right? It's gonna be force of the first element. Let's do the math. It's from force from nodes 1 to 2 of the first element. So it's this number, negative 198.31 times 3 times 10 to the negative 4. So if you do that, you will get a negative 59,500 newtons, and it's in compression. Okay, same thing. Let me go ahead and pause it, and let me write the rest. All right, cool, we're back. So I just want to go ahead and wrote this stuff down. So for the second one, it's 0 times your area. It's going to be 0 newtons. Third one is 44.6 times 10 to the 6 times your area. That's going to give you 13,400 newtons, and that is in tension. It's positive. What else? We got force 4, right? My bad. I just blinked out. Negative 31.5 times 10 to the 6 times your area. That is going to be negative 9,500 newtons. That's in compression. Force 5, it's negative 191.23 times 10 to the 6 times your area. That is going to be negative 57,400 newtons, and that is in compression. Finally, for 6, that is going to be this number times your area. That is going to be negative 19,000 newtons, right? And in compression. All right, almost there. So we got all the force numbers. So technically this is your answer too. Dang, there's a lot of answers, but Okay, all those. Now, finally, it says verify force equilibrium at nodes 2 and 4. This problem is not hard, it's just long as shit. So we got 6, step 6, right? Going to step 7. Let me go ahead and do node 2 first. So let's go to node 2 right here. So it looks like this. We got negative 50,000, right? 50,000. What else we got? We got one this way, one that way, one that way. So this way, that way, that way. All right, let's do that. What is this first one? This one is from 1 to 2. The force from 1 to 2, that's negative 59,500. And it's in compression. So it's gonna, this is what it means. When it's negative, that means it points into the node. It doesn't mean positive X or Y, negative X or Y. It just means tension, you're pulling away from the node. Compression, you're pushing into the node, okay? So that number, what was it? For 1 to 2, 59,500. So we got 59,500 going in. Then for this top one right here, that is nodes 2 through 4. So what's the 2 through 4 force? This one right here, negative 9,500, and it's pushing in. So 9,500. Finally, the next one from 2 to 3. So we're gonna get the force number from 2 to 3, that one right here. That's force 3. 13,400 in tension. So it's pulling away from the node. So it's 13,400. Let me look at my paper, make sure I got that right. Because I'm kind of doing this problem as I go too. Yep, that looks good. So we sum the forces in the X and Y direction. And they should equal 0 or be close to 0. Okay? We don't set it equal to 0, it's just they should be equal to 0. Okay. In the X direction, you have positive 13,400, but this angle was 45, remember, right? If you look at your diagram. So it's cosine 45 plus, minus, 9,500, right? Going in the negative X direction. And if you do the math, yeah, you'll get close to 0. I forgot what the exact number was, but relative to these huge numbers, it's close to 0. Sum of the forces in the Y should be 0. Not equal to 0, just should be 0 again. So we got 59,500 going perfectly up. Minus 50,000. Just like that. Just do the math, it's 9,500 right here, right? And then minus 13,400 sine 45. It's the same exact equation, right? Sine 45, cosine's the same. 13,400 minus 9,500. Here's the opposite. Yeah, it's equal to 0 or fairly close. Now the reason, just FYI, I forgot to mention too, these numbers were rounded. Okay, just FYI, make it look nicer. They were like off by like 50 newtons each one, but it's all good. And it doesn't really matter, right? Well, actually it does, but you know what I mean. You got to know when to be like it's like a safe bet to round. But yeah, in that case, we're dealing with like 14,000, 60,000. If you round it up 50 newtons, you'll be all right. Node 4. So that means we verified nodal equilibrium, whatever, force equilibrium at node 2. Now let's do it at node 4. But node 4 has all this going on too, okay? So you got to take that into account. So node 4 has this going down. Technically, yeah, it's just 50,000. Remember, we split it up, but when you're taking into account both sides, it's 100,000. Okay, so we got that one. We got one going this way, going this way, going this way, going this way, and going this way. All right, so it's 100,000 right here. From 2 to 4, what was it? And hold on, before I continue, I know I mentioned 19,000 would be cut in half, but no. Technically, we just leave it like that for now. It just gets doubled. I would cut it in half maybe just to be safe, right? Yeah, I would cut it in half actually. So it's gonna be negative 9,500, same as this one. So let's go ahead and do that. There we go. All right, there we go. I just plugged it in. Negative 9,500. Because yeah, forgot to divide by 2, and technically, yeah, we have to do that. But when you do it here, so it's negative 9,500, so that means it's pointing into it, right? From 3 to 4, node 3 to 4, it's pointing into the node 9,500. But when you take into account both sides, you'll get a 19,000, and it's going in. Okay, so we got these two. Now let's look at, again, that was from 3 to 4, so now we're going from 2 to 4. Let's do that one. 2 to 4, that is this one, negative 9,500. So from both sides, it's pointing in. Negative 9,500. Well, it becomes positive because it's pointing in now. Okay, so those two. Then finally, from 1 to 4 is the same as 5 to 4. So let's look at that, right? Remember, 5 to 4, this one right here, which is element 5, 1 to 4, negative 57,400. So it's positive 57,400. Pointing into the node. Same thing here, 57,400. So now we got to do the summation just like we did here, right? Forces in the x and the y. But just by looking at the x, we don't need to, right? This 9,500 cancels with this one, and this negative 57,400 cancels with this one, the x components. So yeah, some of the forces in the x direction equals 0. Check. Now some of the forces in the y. So we got positive 19,000 minus 100,000 plus 2 times 57,400, that is sine 45. And yeah, if you do the math, you will get close to 0, if not 0. I mean, but yeah, that's pretty much it. It's a long problem, but it's really is a exam problem. So just really study and make sure you know what you're doing. It's really easy. If he tells you, if you mess up somewhere here, it's really easy to like fight it. Just be like, hey, you know, all this is FEA except this. Really, this is just algebra. So I mean, yeah, you messed up, big deal, but it's like it shouldn't be worth a lot of points because that's just like a mathematical error. All the rest is FEA. So yeah, you can't mess up the rest. But this step particular, when you're trying to find the unknowns, that's algebra. That's systems of equations. So don't sweat it, even if you do mess up. Some professors are just an asshole like that. But some of them are cool. Mine was cool. If you tell him you messed up like that, he'll just take away like half a point out of 30. So it'll be pretty cool. But yeah, that's the top right here, bottom, and the top and the bottom.